Everybody hear me okay? Good morning. Well, a couple ground rules. If you have any questions, please feel free to ask. I'm just here to help outline the differences between your normal gas station and all of these idiosyncratic, unique emergency generator sites that we have. So the title of the session today is Follow the Pipe, and when Leon and I discussed this, we thought, well, where does the pipe go? Where does it come from, and what does it do? And that's an interesting way to look at this because emergency generator systems are unique. They're unique in the design phase, they're unique in the facility requirements. They're not so unique in materials. They're not so unique in plan check. Materials are the same as at a gas station. 30,000 gallon Xerxes, Coflex pipe, Western or Bravo sumps, Vita root or Incon leak detection. Everything's pretty much the same. If you do a file review and we look at Form A, it looks the same. Form B pretty much looks the same. If you can get a peek at a Form C, you can start to see the differences. If you look at a monitoring plan, you can see some differences, and the response plan is the same too. So on paper, even on drawings, emergency generator systems look the same, but they really aren't. And so what we tried to do here for you is to outline those differences and approach it from the system back to the inspection. And then in the second half of the session, it will be discussed from the inspection forward. So please feel free to ask any questions. I think we have time this morning to go back and forth on this if you have any questions. So to get started, we can talk about the contrast between a gas station system and an emergency generator system. We can talk about the configuration. Why is it different? Why does it have to be different? And if you'd like, we can get into some of the technical details of, why a pressure system versus a suction system? And what are the PLLD implications to that? What are the inspection implications to that? The requirements, the testing, the environmental risk implications. And then controls, completely different. In a gas station, you just have turbines and you have the smart controllers. But at an emergency generator system, if it's a pressure system, you have much more elaborate controls. And what do those controls mean and what do they do? And do they have implications to the system from a compliance perspective? And then the considerations, above ground piping, pressure system, PLLD, annual line test. This is just assuming that we're not comparing single wall systems to double wall. If we can just move past that, I think we all pretty much know that consideration. But when we look at a current system, a VPH or even a continuously monitored double wall system, you can see there's some pretty big differences. And then a lot of discussion is with OSHPOD. Who is OSHPOD? Does anybody know what OSHPOD is? Anybody? Help? No. Excellent. Then we'll talk about OSHPOD because this is very important when we look at a hospital system. Fair enough? Okay, so just to get started, common ground, SB 989. We all have to do it. What's the big deal? Well, the big deal to us in the emergency generator business is very clear. When you look at a gas station, heck, the fuel and the tanks that hold the fuel, that's the whole purpose of the gas station besides the hamburgers in the mart, right? So it gets all the attention. It's the beginning of the design. It's the basis of the design with the dispensers. Everything else moves around that. And these are just examples, of course, of the hardscape. But that's not what we look at, not at all. When we're in the design phase, we're looking at trees, we're looking at aesthetics, we're looking at dirt, we're looking at mounds of grass, we're looking at softscape. We have so many great photos, and I wanted to pick the best ones for you if you don't mind. Take a look at this guy. This sump and this pipe is this system right here. These are poplar trees. Now, I don't know anything about trees, but I learned a lot about poplar trees. And the reason I learned about poplar trees is that all these roots are growing right across the top of the tank. And I learned that poplar tree roots are about that deep. They go that way, they don't go that way. So how the heck did these poplar trees get into our underground storage tank? Well, this is a data center. And so the designers of the data center, they're designing data movement and storage. The tank is an appendage. It's not like a gas station where it's the whole purpose of the system. So now we have aesthetics. We have where the heck to put the darn thing. Can we squeeze it in between the building and the sidewalk? Now we need to make it pretty. So you notice there's no pad. Okay, so maybe they worked on the ballast okay to make the tank hold down okay, but there's no pad. So now we need to sort of block the building out from the street because city zoning wants that. Okay, let's put poplar trees in. Okay, well now after 3 or 4 years, I have sumps moving, I have pipe moving, I'm failing my 989. Oh man, now what do we do? You don't see this at a gas station, I don't think, do you? No. So this is a really big consideration. I mean, when 989 came out in 02, we had almost like 75% failures. 05, 55%. 08, down to 40. And now 10, maybe, something like that. And that's just primarily due to age of fiberglass, glue and epoxy and things like that. We've gotten rid of all of these type considerations. So that's what this site looks like now. Get rid of the trees, put a nice big pad on, put a slurry cap over the pipe, and protect the system. So follow the pipe. Where is the pipe? In a gas station, you can pretty much tell where the pipe is. But in emergency generator systems, sometimes we have no idea where the pipe is underground. Does that make sense? Can you see the photos okay from back there? Okay. So the point is that we're vulnerable. We're vulnerable to 989. Well, two 20Ks side by side feeding these generators, but I bet you couldn't tell where the pipe is. We failed the 02 989, and when we dug it up, it was in a planter and a beautiful pickaxe right through the secondary. Because landscape is out there, you know, making everything look pretty. They have no idea the pipe is 18 inches below. No slurry cap over the top, nothing. Just the requisite gravel, and that's it. This site here is down here in Orange County. Very pretty site, and it's right out in the middle of where all of the, we call them patients, can see everything. They don't want a big slab. So beautiful grass area, but you can't tell where the pipe is. Can't tell where the remote fill is. So a contractor coming in to install a new gas line or new electrical conduit or whatever, they have no idea what's under the ground. So this vulnerability is a big difference between gas station and emergency generator site. This site right here is in downtown San Francisco. There's a 15K tucked right underneath that planter. In the 05 989, the landscape crew had a work order that morning because this tree had a branch that was hanging over this sidewalk. So the work order said, get that branch off of the sidewalk before it hits somebody in the head. So they go out and figure out how to do this. So they grab a 3/8 inch cable and a piece of rebar, and they attach it to the tree limb, and they take the rebar and they pound the rebar down into the ground, and they nicked the primary but went right through the secondary. So what's even worse here is that that was the supply line. So now when we go to fix that, we have to take the whole system down. So now we have temporary fuel, or we have an emergency generator backup, and it just spirals out of control from there. So, oh, these are the examples. There's that piece of rebar that he stuck through the secondary. Here's a contractor who was putting in fire cabinets and putting in the grounding rods, and the tank was right on the other side of the wall. He had no idea what tank was there, and he just poked holes right along the tank. This was just a fence post. See the fence up here, the fence post? They just dropped it right down. Fortunately, they didn't hit the primary, but they nicked the secondary pretty good. So this is the vulnerability part based on aesthetics, location. We're in a whole different world there. So what are the main comparisons then, just to kind of set the tone for the rest of the morning? You have one-way fuel conveyance typically in a gas station. The fuel's going to the dispenser and that's it. We have return fuel in the emergency generator business. And I'll show you that with the day tanks, that we need to create a loop. If something happens at that day tank, we need to get that fuel back to the tank. And that return line has some issues to it in terms of regulatory compliance. PLLD on a turbine for a gas station, pretty standard, right? Positive shutdown of the turbine on an alarm or failed test, pretty standard. Well, we can't have that in a life safety emergency generator system. So now PLLDs have a major role to play in design, in compliance, in operations. A minor thing, on the surface it's minor. Turbine and a smart controller, right? Smart controller algorithm has a key in it that has a runtime duration shutoff, because typical filling of a vehicle, even 2-3 minutes. So if that setting is too short and you have that smart controller in a hospital or a data center or a bank, and it cuts off the flow of fuel because the runtime is too long, now we have a problem. Multiple tanks and versus a single tank. And this has implications too. It has implications to VPH, particularly vacuum, on how many turbines do we have and which turbines are running the vacuum replenishment. Tremendous considerations, and when you think of it moving into the system as an inspector or coming into an inspection, these things are all sort of behind the scenes because all the paperwork essentially looks the same. So this is basic now. I'll run through this unless you have any questions. I'm sure you're all familiar with this, but what we have is all the same system. You have a main tank, and this is what I'm referring to on the overflow or the return. Return line is sort of a misnomer. Normally there's no fuel in that line. It is a return line, but these aren't recirculating systems. It's really an overflow line. It's really an emergency line, because you'd only ever have fuel in this if this day tank overflowed. The day tank is designed to shut the pumps off once it hits, let's pick 90% or so. So this is really an overflow line, although we commonly refer to it as a return line. And then your second loop is simply between the day tank and the generator. Not a big deal unless you are considering single wall pipe or double wall pipe. Another design and regulatory compliance consideration in the design phase and the operations phase. So again, this is just a day tank. This is an interior day tank, so how do we meet secondary containment requirements? We have a basin. We can have day tanks outside, and the secondary containment is enclosed. It's watertight, and then the sensors discount that. So any questions so far? Pretty basic stuff. The day tank really is the key. Yes, sir?
What did you say about secondary containment for day tanks?
Yeah, older day tanks are grandfathered in until you hit a point of repair or replacement, but day tanks are required to have secondary containment with a sensor. And this is an open, there are really just two types. This is an open basin because it's indoors, so you're not worried about rainwater. But day tanks that are outside have an enclosed secondary so that you don't have to deal with the rainwater. Yeah, fire code. Just to put it in here, this is a return pump. Sometimes you'll see a return pump, sometimes you won't. You see a return pump when you either have to travel a long distance or you have to overcome an elevation to get back to the underground or even an above ground tank. More preferable is just gravity return or overflow. So if the day tank comes up and it overflows, you just have gravity flow back. Regulatory compliance implication, is that a pressurized line? Yes, I heard yes and I heard no. So to speed things up, the argument for yes is it's initiated with a pump. The argument against it is line's not under pressure, because this is an open line back to the underground tank. The fuel would just flow into the underground tank. There's no back pressure. It's just initiating the flow. But it is an interesting discussion. So real quick, I don't want to go too far down into the configuration, but you'd ask, what could cause a failure here? These are the day tank switches. These are the switches that make the whole system work. The high-level switches fight to turn the pump off, and the low-level switches fight to turn the pump on. So if these high-level switches here, 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 if they fail, you have fuel flowing into the day tank unabated, and it has to have somewhere to go. So just from an environmental risk perspective, this probably is the greatest risk, aside from that discussion of guys poking a hole in the pipe out in the landscape work. So this is just another example of day tank switches. So we fight hard to turn that pump off on the high side. We have a lot of backup because this is what we worry about on the environmental side. On the operational side, we're fighting to turn the pump on because we need to keep the generator day tank full of fuel. So controls, what's the big deal with controls? So on the surface, let's pick Veeder-Root or Incon on the right, and you have fuel controls on the left. Here you've got the smart controllers underneath. So in a vacuum system, the Veeder-Root in this case is turning the turbines on for vacuum replenishment. In this case, the controller on the left is also turning the turbines on for fuel delivery. So those are two interesting items. So you obviously know that the vacuum replenishment is done by the turbines pulling double duty, right? So where does that line get drawn between fuel delivery and leak detection? This is very important to us in terms of making sure that these two systems are kept separate and that their functionality is kept separate. And it also leads into the discussion of PLLD, because the PLLD in and of itself I don't think is really that big of an issue, but the positive shutdown aspect of PLLD is an enormous issue. So that's where this comes into play of how to make that work between leak detection systems, control systems, PLLD, turbines, vacuum replenishment. Another little twist is that for redundancy purposes, you normally have two turbines. So that adds another layer of complexity of, well, if I have two turbines and I have two turbines for redundancy, there are two features that go with those two turbines in our business. One is lead lag. That is, if you have turbine A and you have turbine B, and turbine A is the one that's up to run, and it has some sort of problem, the system will wait a little bit, whether it's the day tank level or timers or other ways to monitor this. And if it's not keeping up with the replenishment, turbine B will kick in to pick up the slack. Well, a problem is on the vacuum replenishment, if only A is set up for vacuum replenishment, but turbine B is set up for fuel delivery. Now, how do you get your vacuum replenished? Another feature, major feature, is alternation. You want to give both turbines equal duty over the life of the system. So if turbine A is up, turbine B is waiting, or vice versa, it all depends on how the vacuum is set up. So this is a big deal in 2481 on how this whole system is set up. And again, in plan check or paperwork review or things like that, none of this really is in there. This is deep into the electrical schematics. Very difficult to see before the fact. So when an owner looks to design a system or how they're viewing this, they have some pretty big decisions to make. What is their system? Is it a boiler system? Is it a generator system? So can anybody help me? Why would this matter? If I'm feeding boilers, why would this matter to the regulatory community? I'm sorry? PLLD exemption? Okay, so what is the definition of an emergency generator system? It's a system that stores number 2 diesel fuel solely for the purposes of running an emergency generator. So it's very easy to see then we have to treat the boiler system differently than the generator system. So now on above ground piping, how do I design that? The argument is sort of fire versus health in a way. It's, hey, I want to be able to see the pipe. I want to be able to look at that primary and inspect it and make sure the welds are good, all the unions are good. I want to look at it every day and make sure. Well, the counter argument is, no, if it leaks, I want to be able to contain the leak. I want to have the pipe sloped, and I want to send it back to a sensor. Okay, so then you get into the definition of an underground storage tank system. What is that definition? Where does it stop? Does it stop where the pipe daylights at the transition sump? Does it stop at the application? So what do we follow here? And what is the better argument? And then, even to me, more important is this a pressure system or is this a suction system? Because this is the number one item. We design a lot of brand new systems, and the number one question that we ask is this going to be pressure or suction? Because everything tends to fall out from there. Vacuum versus hydrostatic. A big controller for the turbines versus integrated suction pump controls on the day tank. This is the biggest question we have. And it goes to that point about the return pump. Can I maintain that as hydrostatic and not have to deal with the vacuum? If that gets defined as a gravity or free flow, not a pressurized line, okay, great. Now I can double contain with hydrostatic and I'm in much better shape. So this is the number one question of a designer is what kind of system does this need to be? Because I really don't want to get into the PLLD issue. I don't want to deal with precision line testing, really. I certainly don't want to have to argue positive shutdown. So if I have a suction system, all of that stuff goes away. And then I have a sheet on OSHPOD, and I can talk to you a little bit about that too. So again, this is the key word to us, and I agree. It goes to exemption and how we're looking at the system. And then this follows in the discussion of how's this system going to look? What's it going to look like above ground? And there's a little twist here too, because if I have this correct, if you look at the exemption, it calls for daily inspection of the piping. So do I have this correct? That if you're under the PLLD emergency generator exemption, you're replacing that with two things, precision line test and daily inspection. So now this, you could have to infer that this is not applying to pressurized pipe. This is applying to suction pipe. So now we have to modify this to say, well, no, I need to meet the exemption requirements. So now we're over into daily inspection. So then that can carry over into perhaps a discussion of single wall versus double wall. Yes?
Can you use alarms in lieu of positive shutdown so that affiliates have an idea that there's a leak somewhere?
Well, you sure can. And certainly underground, that's already covered, right? And so above ground, that's the gist of this argument. If we're single wall, you may have floor alarms maybe. You may be using a room as secondary containment, but that's still the same argument. But I think there's a photo here. Let me jump to that. If you look at this big room, these are the transition sumps from tank A, tank B, and all of this piping, which is substantial, is all single wall. So there's really no alarm associated with that. And again, this is the thing about pressure versus suction. I mean, if we're coming in at 25 GPM off of a turbine, that's a lot of fuel. If you poke a hole in a suction line, what happens? You're just going to potentially lose the fuel on the high side that drains to the hole. This fuel is going to stay right where it is, and the pump's going to cavitate, so you won't be moving much fuel. You're in a way, much, much safer. But if I've got twin turbines in here coming in at 25 GPM, right? That's an enormous difference. Because when I go to restrict the flow as it's coming into the day tank, and I restrict that flow, let's say, down to 10 GPM, that's not going to matter because this is upstream of that. So in working with fire, normally what we just have here is an emergency shutoff and a daily inspection, and that tends to be the common solution to this. Does that answer your question? Here's another example of extreme double wall. So one issue that we have is, okay, if we are in a jurisdiction for double wall pipe above ground, how far do we take that? Just in our experience, typically that ends before valves and gauges at the back of the day tank. But in this case, we actually had to custom make baskets. And we hinged them to the back of the day tank and put a 208 in there so that we could monitor all the valves and gauges. And similarly, you see the filter system here at this same site at the generator. We custom built some trays down there to capture that with a sensor in there too. So that's the difference between the single wall and the double wall. You know, I was really hoping in the back you could see this. I took this photo myself because I couldn't believe it. We installed a brand new system. It was all up and running, and we were demoing the old system. And we wanted to test the line just to see where we were before we demoed it. And there is a tiny pinhole right there, and you can see it was just starting. So that's a live leak in real time occurring in an old above ground pipe that was in a trench under a grate that, you know, who knows, real close. Another year, and a pressure system. I mean, you can literally see the pressure. Can you see that in the back? Can you just sort of see the outline of the fuel coming down? It's extraordinary. So another interesting question, sort of aside from design, is inspecting that pipe. You know, sometimes it's under huge grates, big, heavy grates, and you have dissimilar metals with the unistrut clamps, and you're kind of set up for corrosion, and you can have some condensation. So this is a really interesting implication to above ground. You can just see the pinhole there after we got the pipe out, what was going on. So fortunately, you know, this is a tiny, tiny, tiny release, so to speak, but all it was a thimbleful of sand. We just got there in time. So I don't want to harp on this too much unless you're really interested in this, but this is the big deal for us, is pressure versus suction. So and mainly we put this in if you wanted to just have the sheet or just as a reference if it worked. These are the things that we look at. So is everybody happy with the vacuum? Have you guys had troubles with vacuum? Okay, I see a lot of head shaking. So yeah, I mean, the vacuum's tough. Vacuum is hard to control. And of course, the engineering comes first. If we need pressure, fine, then it's a done deal. But certainly, given a choice, we'd much rather just go with the hydrostatic. The tank is wet, the sumps are wet, piping's wet. We live with a few burps, right, in the beginning. We fill it from the bottom, and everybody's happy, and we just go on. So now, since '04, we probably put in a dozen hospital sites, 2481, and the hydrostatics, no alarms. And the vacuums, it's kind of tough. And then, of course, from the vacuum, we have the PLLD issue, positive shutdown issue, and it just kind of goes from there. Is this okay? Is all this helpful? Good. So why do I worry so much about PLLD? Dispenser's nice to test against. It's set up for that, right? So it's no big deal. Tried and true, been done however many thousands of times. But in our business, what do we test against? So pretty much we have to test against the solenoid valve that really is used to control the fuel flow. And that can be problematic because if that solenoid valve, if its main purpose in life is to open the line to allow the fuel to come in, and its secondary purpose in life is to be closed to allow the PLLD, I think you can see the instant conflict. What if I want the line open for fuel, but the VITA root wants it closed for a line test? I've got a conflict. And that's what happened here. We had a down hospital because of that conflict. And it goes back to that photo of where you have the controller on the left, the VITA root on the right, and the smart controllers below. That's what I meant by that. So if we set up that conflict along with the turbine A, B, and running and not running and backup, there's some issues there. So, way back when we were looking at the, I think it was 2646 then on the exemption, and the rationale, we needed to sort of put it in common terms for the owner to understand. I think it was more than a couple inspectors said, well, in this case, life safety trumps environmental safety. And so that's the rationale for the exemption. So we try to stick to that and then build in safeguards behind it, because obviously we're not going to turn our back on environmental safety, but we want to do the best that we can. So this is probably the worst example we have of that conflict I just said between the controller and the leak detection. This is red dyed fuel all over. This is a 12K above ground storage tank, but it doesn't matter. And there was a conflict, and they were probably 30 seconds from this fuel under pressure climbing over the berm or the sill on the door that was built for secondary containment. The guard, there's a sensor, fortunately, right in the corner right there. And the guard heard the sensor remotely enunciated through the overfill alarm and knew how to shut the system off. If he was over on the other end of the property doing something else, that tank would have emptied, and this stuff would have gotten into the bay. So this is the right side of the generator. This is the back side. Here's all the pumps. There's the AST. You can see it's up on a hill, and right down is the ocean right here. And there's the culprit right there, is this conflict in leak detection versus...
Was that a failure of the high level alarm though?
It was a multiple failure. The root cause was that the high level switch failed, but there was a return line, there is a return line, but the controls failed to turn on the return pumps. So when the fuel climbed up and just climbed over to the return pump, it could go no further, and it actually exited through a local spill bucket that they had put on in case you wanted to feed the belly tank directly. That's where it came out. It popped the cap right off and went right onto the floor. This was really close. This would have been really bad. And this happened to UC Berkeley too on December 9th, a year ago. You probably heard about this, exact same thing. Return pump, high level switch failed, return pump failed, fuel got into Strawberry Creek at UC Berkeley, right up by the stadium, and made it to the bay. Exact same thing. Okay, so this is an interesting one. You can see our little friend here. Can you all see that guy back there? It's kind of far away, but it's our friendly bat. You can see his life spread out all over the wall up here from a whole nest of bats. This is way up on top of a mountain. So an unmanned facility. It's not a hospital, it's not a data center. This is a repeater site for all of the South Bay and Northern California TV and radio stations. So this is another twist to emergency generators. So the bats and the rats and everyone else got in and chewed up all the nylon and the coating outside of the wiring in the day tank. So we have risks in emergency generators that even a card lock that is unmanned doesn't have, because they're built like a gas station. And the designers of these places, you know, they don't think about all this stuff. We come in after, you know, and so we have to think about this. So we're going to redo this entire site. You can see the corrosion. Whoops, sorry. I gave it away. You can see the corrosion on the above ground storage tank. Okay, that's not good. You can see this classic dilemma of above ground pipe outside, the UV issue with fiberglass, the cost issue with steel, big mess. All right, so what do? You paint the fiberglass, and then what happens? You know, the paint's not going to last. Then the rosins in the fiberglass disintegrate, and now you're just nowhere again. So this will all be redone, but true story, that's the guy right there. That's the guy and his family who caused this whole problem. All right, so I already showed you the next one. This guy caused a problem too. We had a day tank overflow because a swarm of wasps built their nest in the vent line. And they built it so strong that they obstructed the vent line completely. So there was no escape, and the fuel backed up and went right out the vent line. It's weird things can happen. Okay, so I'll save a few minutes just in case you have any questions, but what is OSHPOD? OSHPOD is really very straightforward. It's the Office of Statewide Healthcare Planning and Development, based in Sacramento. They oversee everything a hospital does, everything. So what are the implications to us? OSHPOD, for example, when we go to build a new system at a hospital, we get all of our drawings done to your satisfaction. We turn them in to you. OSHPOD, as a state permitting agency, relies on you to deal with 2481 and VPH and, you know, making sure that all the LG is correct and everything is good. But what they're interested in, on top of that, and they rely on you to take care of all of that detail, is, structural. And this is what they're worried about. So we spend months with them on the pad, the straps. I could go on and on about what they look at. They peel back the layers of the onion all the way to going to Xerxes and wanting a mill cert on the epoxy that they use back when the fiberglass was mixed. They wanted a mill cert on the rebar in the deadman. So pretty tough on us. But the point is that they're interested in the long-term stability of the hospital, structural, electrical, fire life safety. That's what they're interested in. They're interested in the runtime that we're giving them for the generators and the boilers. So it's a dual permitting that we have. And then when it comes time for inspection, they've inspected the installation all along. They usually dovetail their inspections with yours on, you know, primary, secondary, and the tank, and ELD or whatever, and then it all comes together at the end. So OSHPOD does not replace Coupa. They are just sitting on top of the hospital, making sure that all of these 5 disciplines are met to their satisfaction.
Sometimes they forget us.
Yeah. Sometimes they do. And sometimes there's this, but we try to get in the middle of that.
Sorry if I missed it, but what is the criteria or the main reason why some generator tanks are vacuum versus pressure? What's the deal?
Why some tanks are vacuum?
Versus pressure systems on generator tanks.
The tanks themselves?
Yeah.
Steel tank won't handle hydrostatic. So if you got a steel tank, you automatically default to vacuum. But if we have a fiberglass tank, we don't see any reason to go vacuum there. Is that maybe what you're referring to? Okay.
I've got 2 questions. On your pressurized return line, do you need a line leak detector or do the line tests, tightness tests?
Well, you know, fortunately, we have not been asked to treat a return line with a pump as a pressurized line. So we haven't been tested to that.
Okay.
Yeah, but it seems like for OSHPOD, they have to meet the requirements for boilers or hot water as well as power. It seems like what I'm seeing with plans. I don't know OSHPOD, but I'm assuming that's the case. Is that what you're seeing, that the hospitals want to meet both requirements with one generator, and therefore we're having issue with the leak detection issue? So do you see that there might be some movement to try to change that so that it actually is based on now versus, when it was written?
Well, that's a really good question. Do I have time for that? Okay. So the question is, if you're feeding a boiler system and a generator system, you got a number of considerations. First of all, the generators are required to have a minimum 72 hours runtime. So you do a straight calculation of generator consumption at full rated load. We need to make a decision on fuel capacity for the generators first. So with a 72-hour runtime minimum, we do that calculation. If there's enough room left over in a single tank, obviously the owner would want to feed the boilers off that single tank rather than buy a separate tank. I mean, that's pretty obvious. So we would limit the drop tube in that tank so the boiler pickup could not get down into the generator fuel. That doesn't address the regulatory issue, but it's normally what they want to do. What we've begun doing is building a compartmented tank. We have one right now, so we've met the requirements for the generator fuel capacity, added on 5,000 more in a second compartment, and we'll just treat it as a second tank. A little bit of a premium also, obviously, for building a compartmentalized tank. We have another probe, another sump, another turbine, but that's far less than compared to a whole separate system. So that's sort of a middle ground. But your question is very good. How do you address this, and can we sort of avoid the regulatory conflict in design? I think that's our best way, is to just use the compartmented tank. Oh.
In the past, on some older hospitals, I actually have piping going through walls. Have piping going through walls with no, you're not going to have any visual at all. I never could figure out the justification. They used to always say it was because of OSHPOD regulations. Has that changed, or is that still legal?
So your question is above ground pipe going through walls?
Like in the walls themselves, so you have no visual.
Oh, I see. So in a plenum space, hidden. Well, normally in a central plant, you have, you're just coming in like the photo. But, so I don't know. I don't know that there's been any special consideration to getting hidden. Normally, just the tank is there, the transition sump is there, and the pipe's right there. I don't know that there's anything special about a plenum space. Okay, any other questions? Well, thank you very much.
So again, my name's Leon Worsham. I'm with San Diego County Environmental Health. I do hazmat compliance inspections. I also do after-hours emergency response. This is a case study that I just put together because it was a lot of work, and we learned a lot on how to inspect and determine compliance for emergency generator tank systems. That's my one of my inspectors in my group, so when she saw some problems, she brought them to me, and they became my problem. So 15 years doing this. I had the military route for 5 years. I've seen every type of monitoring in Title 23 except for manual tank gauging. Other than that, I've seen every weird thing out there. I like the weird systems. They're more entertaining for me. So this is what the environmental compliance group from Tate Environmental said is the most complex generator tank system in the state. So I'm going to skip through a lot of slides and not tell you every detail on how the system works. I just want you to see the process for how we went through to figure out compliance. And if you have any questions, raise your hand, holler. If I'm looking the wrong way, shout real loud. So these type of systems you know, they're not your gas station. You figured that out already. There's some of the places I see them. My current route, I have 9 hospitals. I have some that have generators and boilers, which present their own weird, unique issues. If we have time, maybe we can talk about some of that again later. Military, prison, I've done some prison facilities and have universities, so we'll see if my voice can make it. One of the problems that we have when we're going out and looking at these sites is we get different people. We have different inspectors, different people doing repair inspections versus compliance inspections. We have different operators, environmental compliance technicians. So information is lost. There's a lot of miscommunication, sometimes bad as-builts, and then some really complex piping systems and the weird exemptions. So one of the problems we have in our group is, you know, we're all EH&Ss. Not everyone has a thorough understanding of how systems work. Like, I used to be a plumber and I installed septic systems. My dad's out on a backhoe right now somewhere, digging a hole somewhere. And so I have a little bit of a concept of plumbing and how things are piped together, which I think helps me. So not everyone in my group has that experience. You've already seen this. It's solely in connection with an emergency generator tank system, and diesel fuel. The ATT site that I'm going to walk you through real quick, I'm just starting out like I'm at my desk and here's my lead specialist calling me from the field going, what am I looking at? So my instructions to her were, you know, take some pictures and follow the pipe. So she did. She took some pictures, she came back, brought them, we looked through them. Underneath the ground there's a couple compartmentalized tanks. She wondered, is this a fill or a pipe sump? And yes, it's both, because that's how these type of systems work. I don't think she really said, I see a red thingy, but she may have. So you can see the turbine for a pressurized system. Where do the pipes go? In this case, she's just following what the technician told her is the pipe. She looked at the main tanks. They took her over to some day tanks. The day tanks are underground in the planters here. Then there's some more sumps for the day tanks and even a transition sump. So it gets hard when you try to follow the pipe. It's hard to tell where it goes. You can see, most of you in here probably know, you know, there's probably some supply and return piping there. Hard to tell what some of these other things go to. Transition sumps. In the basement, there are sensors. Instead of doing visual of every component everywhere, they set sensors up and the piping goes through the wall. Metal housing holds sensors. Back out the wall, there's some more penetrations. Piping everywhere, no clue what it goes to or how it's really connected. More piping. This is next to the day tanks, outside the wall from the day tanks. It comes in, and I'll run you through the system in more detail in a second, but this is just what the inspector brought back and scratching her head going, what is going on here? How do we figure out if this system's compliant, and where does the piping end? Like our oversight. And we've had discussions with contractors over the years and even in-house, and sometimes the fire will oversee pipe, and we'll also oversee the pipe because of the definition for underground storage tank system. Again, pipes connected thereto, below the surface of the ground. In this case, these pipes usually will end at a day tank, a belly tank, or the generator itself. And at that point, when the piping from the underground tank is now attached to an above ground tank, that's where we stop looking at it. So that's where the fire code will kick in. Like Bud showed you some pictures of piping connected to a day tank, and he had some containment berms in there. That was probably, he thought that was fire code. Sometimes a fire marshal will say he wants secondary containment. And we already went through this, the weird exemption for unburied fuel piping. They must do the visual inspections when it's operated, but not less than monthly. I wasn't aware that was a pressure only. It does make sense. However, it doesn't say that there, so. And sometimes we run across these weird systems. I just bring this up because the same logic applies right here for vaulted tank exemptions. It includes the connected piping. So my specialist brought back all that information, the pictures, and we had to try and sort it out. So we went through our records and our scan files, and we looked at SB 989 reports, we looked at diagrams, we have scanned files, inspection notes, trying to figure it out. And this is what the secondary containment testing report looked like. There are a lot of components. And in case you're aware, there's really no requirement to make a plot plan with these. How does that help? So we worked with them. It got better. Again, there was no requirement for them to submit this, and we can't figure out where everything goes. They didn't really know where everything goes either, so we just did some math and said, okay, 37 components here you tested, tell us where these go. So one of the problems we saw, and it wasn't just AT&T's fault, it wasn't the contractor's fault, is we got into this system. In 2004, AT&T worked really hard to get everything all right everywhere because there was some type of enforcement order. I'm not sure the details, but I know they became very helpful, assisting us and giving us whatever we needed. So they did 37 components tested in 04, which would seem like enough. We do annual inspections every year. 07, they tested the same 37 components. What we found is the case is that when a contractor comes out to test components or bid a scope of work, for the most part, they're just pulling up the old record. Well, what did they do last time? It was okay with your agency, so we're going to do these 37 again. Seems fair enough. So that's how it went. They had a few problems. They did some repairs, even got a repair permit. Then 3 years later, the same 37 components, more failures observed. The failure rate, I think, is getting less, but it depends on how old your system is. One of the things I just wanted to point out here is that as we have more repairs, we have whatever inspectors available to go out to do it. So some information, again, lost in translation. So here's just how my specialist that works with me, Hosti, she likes to draw everything out, and this is where we started. Pretty simple, a couple of tanks, got a compartment. It's 2 sumps, an annular sensor for both tanks. Underground day tanks, sumps. That's a piping transition sump. And here's the basement room where all the pipes come from the tanks before they go out to here and back to here and on and on. So we started with that and just decided, all right, let's try and draw it out. So that's the 7 tanks when you're looking at the street. 3 in the planner, and then each of those is 2 compartmental tanks in the loading dock area. So one of the things I brought out to our specialists, and we learned from this process, is that there's a big difference between doing a monitor system certification, witnessing a monitor system cert, and doing a compliance inspection. Watching little buzzers go off is great. It'll tell you that they work, but it doesn't necessarily tell you that they're monitoring everything they need to be monitoring. It doesn't tell you that they have sensors everywhere there needs to be sensors. It's just showing you that the sensors that were installed work. So we need to gain an understanding of how the system works. And then based on the installation date and design, suction, pressure, That's going to determine what the regulatory requirements for us. So we brought my supervisor out. He speaks with a strong accent, so we make fun of him a little bit here and there. He always says English is his second language, and he had a good understanding of underground tanks because he came from site assessment. So he can look at that and see that. People who don't do these inspections all the time, they don't know what it looks like under the ground. So it helps. Of course, this is a different site, but you get the idea. It's hard to visualize. So there's Hosty again asking Richard, nice technician, yes, this is an underground tank, right? Yes. Piping connected to it, yes. Richard was not so happy to be helpful the second or third time out, but he was still very polite. That's a lot of work that they had to do on this site to figure out how everything works. So again, we got to look at all these sumps and figure out how many piping penetrations there are, where do they go? Here's a fill sump. You can see the donuts, so you know that they do secondary containment testing on those. Another pipe sump. I've showed you a lot of pipe sumps now. We only have 2 inspectors in our office that I know would want to see more because they are tank geeks. Like me, I'm trying to get out of hazardous waste and over in the tank track. You guys have to stay here till the end to get your hours. When I teach hazardous waste class, they can leave whenever they want. So you guys are stuck. You already saw what a typical generator day tank looks like. This is their day tanks, underground in the planter and pretty far down below that. Of course, on the other side of this wall, it's a big basement. And here is a metal housing that has all kinds of pipes on it that if we would have just moved it, we probably would have figured a lot out a lot sooner. Piping transition sump, I saw 7. It turned out there was 8. I can't count. They're testing this for our certification, but where do they go? Nobody knew. They actually had to go back and do a whole bunch more line testing to figure out where are the pipes going to and coming from. So again, piping from the bulk tanks in this case went into the basement, then over a transition sump, and back over. The reason that this site is set up like this is they're responsible to keep the dial tone, these ATT sites. And this station here, they wanted every tank to be able to go to every one of the compartmentalized tanks, to be able to feed every one of the day tanks, to be able to feed every one of the generators. So that's why it's such a maze of piping. This is my ugly write-up from when I went out there, trying to figure out where piping went, and it works for me. I don't know how people figure it out if they don't draw some kind of sketch. All right, so getting to the point of our class here, there are lots of piping penetrations. When we followed the pipe around, we found that there are 16 going in this wall from the loading dock area. This sump had, maybe it is 14, 7 on each side. There were 11 more going in this wall here, and there were 8 coming in that wall over there. Lots of piping penetrations. There are 5 penetrations for each tank. There's 3 there and 2 there, along with a vent pipe, which I'm not counting. This tank was installed in '95, so the vent pipes are single wall. And then 3 at each of these, along with the vent pipe that I don't count. So I'm trying to figure out, when I look at my secondary containment test report, how many are supposed to be on there? Are we close? So that was a lot of piping penetrations. They tested 17 pipes. Now, for every pipe test, there's 2 penetrations, right? Normally, unless you use jumpers. You got a pipe here and a pipe here, you do your test. So for every 2 places you see one leaving a tank or coming through a wall, for every 2 there should be 1 test. Here we're asking what pipe is tested, and they finally went through this process, and they gave us very detailed information on what pipe was tested. They gave us a map that showed us pressure lines that they're doing annual integrity testing on. They showed us every line, everywhere, and they gave us more information than we knew what to do with. So be careful what you ask for. You might get it. It was helpful, though, in figuring out how to determine compliance here. So this was their summary saying that we went back to 95, and we can't find in the as-built how these things work. They looked through a lot of records, we looked through a lot of records, and ultimately they just had to spend a lot more time on site. And now we have great records in our file. So you can see how complicated it gets. These are the 3 day tanks in the planter, the raised planter, and then from there we got piping going through walls. There's 11, there's this 5 there, 5 there, 2 there, over to another basement area. Those are the 12 coming from the loading dock. They broke it down into supply, suction, return, pressure, the manifold room. So now we've got pictures in our file. An inspector is going to go out to the site now. We can leave a comment for him and say, hey, look at the file before you go out. Pull this up, look at the photos, look at the explanation, and you'll have a clue on what's going on out there. So out back, a bunch of supply lines, return and overflow. Again, we didn't see this the first time because we didn't know to move the metal covering on the wall, but right there behind it was all this piping coming up. So then that's one side of the wall, and then they tried to put together for us the other side of the wall. Try and give us a visual of where they go. So in this case, when you're putting it all together and trying to figure out how it works, follow the pipe, make the drawing, list the penetrations, but really you need someone to explain the system. And we couldn't do it without them. I have 9 hospitals in my route, and it gets a little weird, but nothing like this. When you see something weird like this, and the SB99 tests don't make you can't tell what the tests go to. I don't see any way to review it unless you get that information. So real quick, I was going to show you counting components. So when you're looking at a secondary containment test and you're looking at your map and you're trying to figure out how many tests should there be on here. Obviously 1 for each annular, 1 for the sumps. The piping has 2 penetrations unless they use jumpers. So you would count all your penetrations, divide by 2, and that should give us our magic number. We're not counting electrical conduit, vents and vapor recovery unless they're installed after July 03. That's what a jumper looks like. They did have a jumper here. So for older systems, jumpers are important. Sometimes they want to leave them in place, but they shouldn't, because you can't get your product to flow back into your sump if the jumpers are left in place. On a newer system, though, if you take that jumper off, you may be disconnecting the vacuum sensor. So now you've just rendered the whole system useless. So know the data of your system and how it works before you tell them what to do with their jumpers that they put on. All right. When I did it at my office, I had a board and I had the audience shout out to me. They were so pumped up. I had them count everything. How many annular sumps and pipes are there? About? Anyone know about where we're at? Or should I just go to the next slide? Sorry. Made you work your brains. There were 78 pipe penetrations. In addition to everything else, the 78 pipe penetrations should have had 39 pipe tests. Plus everything else, 56 test results. And if you remember how many we had 37. So every year we looked at the 37 they sent in and said they look good. Good job. But really, we missed a few. So to point out, they went through, this is their testing of the components that they needed to test. I counted 18 and called them up and harassed them, and that's where they said, no, we used a jumper. We're not cheating. They did it right. And 10 of these failed, so 10 of the components weren't working. They fixed 6 on site and had to get repair permits for 4 of them. And now they're all good. So I think I was trying to show here that the process we went through asking for information and how long it took to get us up to where we need to be. So last year in 2012, all went good. After 9 years of testing, inspections, repairs, we finally got it right. Unfortunately, there's a problem with one of the primary tanks right now, and we're working with them to figure out what the primary tank is, but the piping's good. All right, so I made a simple exercise to put to use what we just learned. All right, this is a very simple generator tank AT&T site. There's a piping sump and a fill sump, an annular sensor. Generator room is to the north here. So there's our pipe sump. See the fill? Annular. All right. Looking in the pipe sump, you can see the penetrations. This was installed in 04, has double wall vent piping. The supply and return are in one line. The fill sump is exactly that, just for filling the tank. So following the pipe, this is what you normally see at a simple site. It just pops out of the ground somewhere, runs across, hits the generator. That's a transition. I mean, you could look at it like a transition sump, but because it is unburied piping, they can visually inspect it, so they don't have to have the sensor in there in this type of transition sump if it's unburied. Supply return, 2 penetrations. So there's the pipe supply and return coming from the tank. Let's see if we can figure out from the site plan how many test results we should see. One annular, 1 pipe sump, 1 fill sump, a double wall vent line, and then the supply return. We're in 1 sleeve. 5 tests. This one actually was a fail, but they fixed it up. So a couple of things as we're finishing up here before the quiz. You'll have to pass a quiz. This was given for our inspectors in-house training, so you get it too. We talked about it earlier with Bud McQuaig. The requirement, even though it's double wall pressurized piping, this is how the regulations are written. An annual integrity test is required. And when you think about it, they don't have fail-safe turbine shutdown or line leak detectors, so it kind of makes sense. But for years, I had overlooked this, thinking double wall piping didn't need this. It's there. Don't forget, annual integrity test. All right, somebody, please help me out here. When does the piping connected to an EGT usually cease to be regulated as underground storage tank piping? Give me some examples. What, someone said when it daylights. What I hear?
Next to an above ground tank.
When it's next to an above ground tank. When it connects. Okay. So daylights, possibly. However, if it daylights and it hasn't yet connected to another tank, above a belly tank, a day tank, it's still part of the UST system and subject to Title 23. However, now you've got all the fire code stuff to deal with too, so now you've got piping that's very regulated. So the day tank, usually, unless your day tank is underground like we just saw in our little scenario, the generator or the belly tank are usually where it's at. sure someone can prove me wrong, but there's probably some other weird situation. How often does the unburied piping connected to the EGT have to be inspected? At least, I heard at least monthly. I heard someone say in the back, when you operate it, but not less than monthly. So sometimes we see people go out and they do a monthly inspection of everything at a system, but they inspect the piping too, like a DO. But that's not the day that's not when they're using it. So they need to time their inspection with actual use so they can see if this thing is leaking or not. The annual, when does it require an annual pipe integrity test? That wasn't meant to say annually. But under what conditions? I'll give it to you. Pressurized piping. Here is what AT&T worked up. I think it's a great little checklist for the unburied piping, and they go through, and this is what they do every time they do their when they operate the pipe. And here's a lot of things to do to figure out how your system works. And there's my credits to AT&T, Tate, and our staff. Thank you for listening. Are there any questions on what I just went through? Sorry, I went through very quickly. All right, you're dismissed. If you have any questions, come on up and see me.